Now the next set of questions was on analysis, a topic many people find quite challenging, especially when they first meet it. This first question is about using the proper formal definition of the limit of a sequence. So it says, what precisely does it mean to say that a sequence of numbers converges to a real number L, and prove using this formal definition. Now you see you do have to use the formal definition. It would not be appropriate here to use standard results about limits. So the proper definition, the formal definition is this. Xn tends to L if for any epsilon there's some n, so that for every little n bigger than capital N, xn minus L is less than epsilon in size. Now, as I mentioned, the question explicitly requires us to use the definition of a limit. Any other approach would be not answering the question. So what that means is we need to actually show this. We need to consider xn minus 2 and show that it can be made less than epsilon for n large enough. So, considering xn minus 2, we can calculate it. It's equal to this expression here. Now, this is a bit of a mess. You would not want to solve directly this inequality less than 2. That would be a horrible, horrible mess. So what we're going to do instead is approximate this expression by something slightly bigger, and then hope that we've done the approximation in such a way that by bounding it by something simpler, bn, it's easy or easier to solve the inequality bn less than epsilon. Now, roughly speaking, we look at this object here and we think, well, it's something like n cubed over 2n4. What if we could get everything on the top being something like n cubed and everything on the bottom being something like n to the 4 or something like this? So we look at it and we say, well, the bottom line is certainly bigger than 2n to the 4, so I can get a less than or equal to here if I simply delete these extra positive terms on the bottom line. On the top line, to get a less than or equal to, get the right inequality, I can't just throw away the 4n squared and the 2, but I can say that 4n squared is no more than 4n cubed and that 2 is no more than 2n cubed. The reason I do that is that the expression then becomes really quite simple because it's just n cubes on the top and n to the 4s on the bottom, which simplifies to give 7 over 2n. Then solving 7 over 2n less than epsilon is extremely easy. It's just n has to be at least 7 over 2 epsilon, and therefore I can take this number here to be n. And that's fine. I don't need to find the smallest capital N. I just need to find a suitable capital N. Next question is find the limit of this sequence of numbers, where the sequence of each member of the sequence, it looks like this. Okay, well, we're going to use the sandwich theorem. It's very straightforward. How many numbers are added up here to give an? N of them. Actually, n plus 1, because it starts with plus n and goes to plus 2n. So n plus 1 numbers altogether. The biggest one is this one, and the smallest one is this one. So that enables us to bound the numbers. Certainly we can easily bound from above because there are n plus 1 numbers here. They're all less than or equal to 1 over n cubed square root. So this gives us this inequality here, which simplifies to this, and that clearly tends to 0. So an is sandwiched between 0 and something that tends to 0. Yeah, we could have been a little bit more precise here. I could have said that an is bounded above by this, and bounded below by this, and then use standard results about limits to show that this tends to 0, this tends to 0. But we don't need to do that. It's actually easier just to observe that none of these numbers is as big as 1 over square root n cubed, and there's n plus 1 of them, so we can get this more direct inequality. The next question is about recursive sequence. The first number is some positive real number, and all subsequent numbers are defined recursively. The first part of the question is by using the inequality a squared plus b squared greater than or equal to 2ab, prove that xn is always at least square root of 2. Okay, there are actually a couple of ways of doing this. Here's one of them. We only need to prove this for n greater than or equal to 2, so we can use the formula for xn in that case. So xn is xn minus 1 squared plus 2 on the top. Now xn minus 1 squared plus 2 can be written as xn minus 1 squared plus square root of 2 squared. And I'm using this because I'm going to use the fact that a squared plus b squared is at least 2ab. So this expression here is at least 2 times xn, taking a to be xn, times square root of 2, taking b to be square root of 2. So this gives this expression here, which simplifies by cancellation to give square root of 2. Sorry, slight typo there, square root of 2. There are other ways of doing it, but that's a fairly good way. So here's the statement again. Now we've got to prove that the sequence is not increasing. xn plus 1 is no more than xn. Okay, so one thing I could do is I could just look at the difference between them and try to show that that is less than or equal to 0. Okay, so what do we know? We know xn plus 1 is given by this expression. If I take away xn, I get this expression. Now, why is that less than or equal to 0? Because of what we've just proved. We've just proved, you see, that xn is at least the square root of 2. So xn squared is at least 2. So this number here, 2 minus xn squared, is less than or equal to 0. And of course the bottom line is non-negative. Another way we could do it is, instead of considering the difference between them like this, I could have said, well, xn plus 1 is no more than this. Again, I'm using the fact that 2 is less than or equal to xn squared, and this is just xn. So we've got the sequence, same sequence that we're dealing with. Now we deduce that it converges and we find its limit. The sequence is bounded below because it's always at least square root of 2 for n greater than or equal to 2, and of course the first term is just some number. And it's decreasing. That's what we proved in the second part. So it follows that it must converge. Now to find its limit, let's call the limit L. Here's the crucial thing. If xn converges to L, so does xn plus 1. But we've got a formula for xn plus 1 in terms of xn. Now, if xn is tending to L, this expression tends to L squared plus 2 divided by 2L. But this xn plus 1 is tending to L, so this number L and this number here must be the same. Now, if you solve this, it's straightforward. You get L squared as 2. Now that, on the face of it, has two possible answers, square root of 2 and minus square root of 2. But all the numbers are positive, so the limit can't be a negative square root of 2. So our conclusion is that the limit is square root of 2. So this recursively defined sequence of numbers converges to the square root of 2.